Hey guys, we are going to be discussing the topic of collision in this video. So what is collision, right? When two objects they come into contact for a short duration of time, okay? So that process where they come into contact is called collision. Okay? Now it's very essential that this coming into contact should be for a very short duration. So that is what essentially is termed collision. Now say I could take my hand and I could go and place it over here. It is coming into contact. Okay, but then this contact is not for a very short duration of time. So this is not going to be termed the collision, this coming into contact. Okay, but when two objects come into contact, stay in contact for a short duration of time, and whatever process is happening is over within a short span. Okay, so and then they either separate apart, or there is a case where they come into contact and they would stay in contact forever. Okay, but then the process of that coming into contact and then staying into contact, that process would be over in a very short duration of time. Okay, where the contact happens for a very short duration of time and the process gets over. Okay, that is termed as a collision. Okay, now here we are going to be taking some idealistic situations. Now say there could be so many different practical examples of collision, like say two asteroids could come and collide with each other. You see so many accidents on the road. Okay? They are all examples of collision taking place. But we are not going to consider those collisions directly over here. We are going to consider simplistic models of two objects which come into contact for a short duration of time. And we are going to consider those objects as being somewhat rigid. So we are not going to consider cases where a car goes and collides with a truck and then that car gets crushed and it becomes dented. Okay, so those kind of cases we are not going to be analyzing over here. It becomes a bit too complex to analyze such situations. Now here we would be analyzing some simple situations where like say two balls come into contact with each other. You take a ball, drop it onto a floor, okay, it goes, collides and bounces back from the floor. You take a ball, project it, so it goes and collides with the floor. Okay, so such cases we are going to be considering in this topic discussion. So we are going to consider simplistic models. Consider a case like this. So that is an object A and there is another object B. So A is moving with velocity u1 and B is moving with velocity u2. Now these two come into contact. That would happen provided u1 is going to be greater than u2. So when this condition is met, these two objects are going to come into contact and then these two collide, and after collision, say the velocity becomes v1 for object A and for object B the velocity becomes v2. And after collision, it would so happen that object B would be moving with a velocity greater than object A. Right? So that is the instant before collision. That's the diagram, and this is the diagram that is there after the collision is over. Okay, this is after the collision. So before collision, u1 will be greater than u2, whereas after collision, v2 will be greater than v1. Okay, now this is a case where it is a direct collision. So I'll also explain what is the difference between a direct collision and an indirect collision. Okay, in a direct collision, which is the diagram that I have drawn over here, two objects, right? One is moving like this, the other is moving like that. Collision takes place, and then B moves with a greater velocity and A moves with a lesser velocity. So this is an example of a direct collision, and I'll explain what this direct collision means. And there is also something called as an indirect collision. Okay, so first I will just mention that statement. You can make note of the statement. Like when the velocity of both the objects that are going to collide, if velocities of those two objects is along the line of impact. Okay, for both the objects, it should be along the line of impact. if the velocities of both the colliding objects is along the line of impact, then such collisions will be termed as direct collision. This is a very trivial case, right, where both the objects are moving like this, they are going to come into contact. So what is this line of impact? A line of impact is the common normal when the two objects are in contact. Let's say, for example, these are the two objects. So this is the common tangent, this line, and this is the common normal. When the two objects come into contact, the common normal that is there, okay, so this one, the common normal is called as the line of impact. And if velocities of both the objects is along the common normal, then in such a situation we call the collision to be a direct collision. Else the collision will be termed as an indirect collision. I'll just draw some examples of direct collision and indirect collision, and then I'll explain certain terms. Okay? So once you understand those terms, you will be able to understand certain specific situations. Okay, alright. So now consider a situation like this. Okay, this is a floor that I am representing, ground. Okay, in one case, you take a ball and you just drop the ball so that it comes and collides with the floor over here. That is situation 1. Okay, in another case, assume that there is a person who has thrown the ball, okay, and say when that ball has been thrown, say that ball travels along this path and then it comes and collides over here. Okay, so this is another example. 2 examples or 2 situations you could say. Okay, one situation is where a ball is dropped, it comes and collides with the floor. Another case where a ball is projected like this, so it moves along this path. The trajectory, from kinematics, which you already studied, that's going to be a parabolic path, and it comes and collides with the floor. So just before the impact takes place, the velocity is in this direction. Okay, now this is a clear example of an indirect collision, where if you draw at the instant of collision, you draw the common normal. So this is the common normal for the object and the ground, that is the ball and the ground, line of impact. And velocity of this ball clearly is not along the line of impact. Since the velocity is not along the line of impact, the second one is an example of an indirect collision. Okay, an indirect collision is also termed as a 2D collision, or also it is termed as an oblique collision. Okay, indirect, oblique, or 2D. Okay, so you can use any one of these 3 terms: indirect collision, oblique collision, 2D collision, or you can use all these 3 interchangeably. Whereas the case where the velocities of both the objects are along the line of impact, in this case, the velocity of the ground is 0. So it is only the object that we are going to consider which moves. So this ball, when it is going to come into contact, it will have a velocity in this direction. Okay, that velocity itself is along the line of impact. So that is a case of a direct collision. A direct, or it is also called as head-on, or it is also called 1D. Okay, all these 3 you can use interchangeably. I will write it here. Okay, so direct, head-on, or 1D you can use interchangeably. Indirect, oblique, 2D you can use interchangeably. All these mean the same, and all these 3 mean the same. Okay, so now we will see certain other terminologies that would be related to collisions. There is something known as speed of separation and speed of approach. And let's try to understand what those terms are with regards to direct as well as with regards to indirect collisions. Right? So let's just get right into that. Okay, so I'll just consider some situations and I'll explain what is meant by speed of separation and what is meant by speed of approach. Okay. Now, what happens before collision is, 2 objects are going to come towards each other, they are going to collide. So, before collision, what happens is approach, and after collision, they are going to move apart. That will be termed as separation. So, the situation that is there before collision, we will have approach, and we will use the terminology speed of approach. So, before collision, we will try to understand what it means in the context of direct and indirect collision. Okay, so, before collision you will have speed of approach, and after collision you will have speed of separation. Alright, now I will just draw some particular examples, some particular situations. So through those examples you will be able to try to understand what is meant by speed of approach and what is speed of separation, the things that happen before collision and after collision. Okay, so I will take a simple situation like this. Okay, so that is an object which is moving with 5 meter per second. Let's say we call this object A, and say we call this object B, and this is moving with a speed of 2 meter per second. Okay, and both are moving in the same direction. So when they come into contact, the velocities of both the objects are going to be along the line of impact. Okay, line of impact is this line, the horizontal line. Okay, and velocities of both along the line of impact. So that's a clear example of a direct collision. Okay, now so you can see that this is a situation before the collision. So this will come and catch up with this. So here this is a case where A is approaching B with a speed of 3 meter per second. Okay, so we'll write speed of approach for this case is 3 meter per second. And after collision, something of this sort could happen. Okay, now B is moving with 4 meter per second, and A moves with a speed of 2 meter per second. Okay, so after collision, A's speed has become 2 and B's speed has become 4. So now you can see that B is moving with a greater speed and A is moving with a lesser speed. So there will be separation which will happen between the two. So this moves greater distance, this moves lesser distance, and the separation between the two will keep on increasing. So after collision, here we have something like the speed of separation. So here the rate at which they separate is 4 minus 2. The speed of separation is 2 meter per second. Alright. So that's a very simple case of 1D collision or a direct collision where we have written speed of approach and speed of separation. Now we'll try to understand how to write speed of approach and speed of separation when there is an indirect collision taking place. Okay, so that is somewhat conceptual. You can try to understand it with the examples that I am going to show. So let's consider a case like this. Say that is a vertical wall. Okay, I'll represent a wall like this. Okay, so that's a vertical wall. And consider a case where there is, say, okay, I'll draw it like, say that's a bullet. Okay, a bullet. Somebody has fired the gun, and then that bullet is, say, moving in this direction over here. Okay, with a speed of, let's say, some 200 meter per second, it is moving in this direction. And there is a wall here. Now, will this bullet move towards the wall when it is having a velocity in this direction? Now you can just see this velocity is not going to take this bullet towards the wall. Okay, so this velocity is not going to bring this bullet closer to the wall. So there is no approach. This velocity does not create an approach between these two objects, but rather, suppose say if you had something of this sort. Okay, there is a ball, say, which is moving in this direction. Let's consider a ball which is moving in this direction with velocity v, where say this angle is theta. Okay. Now when the ball is moving in this direction with velocity v, we can resolve the velocity of this particular ball. Now after some time, say this is going to go and collide. Okay. Now when collision takes place between this ball and this vertical wall, this line, this line over here, this is the line of impact over here. This line, okay, line of impact, I will denote it with LOI. Now LOI stands for line of impact. Alright. Now this ball which is having velocity v, if we resolve this velocity v in two directions, let's say along the line of impact and perpendicular to the line of impact. Okay, so along the line of impact, this has a component of, along the line of impact is the horizontal direction here. Right, so along the line of impact, it is v cos theta, and perpendicular to the line of impact, vector concepts. Okay, so resolve that velocity vector along the line of impact and perpendicular to the line of impact. Right, so that is v sin theta. Alright, so now we can clearly see that if suppose V cos theta was not there, if this component was not there, only this component was there, like the bullet case. Okay, when the bullet was fired, it was moving in this direction. If only this V sin theta is there, then this object will never approach the wall. That is, we are going to say that the velocity which is existing perpendicular to the line of impact, okay, that velocity will not create any approach. It is the velocity which is along the line of impact which will cause approach between the two objects. So it is this component which causes approach between these two. So for this particular example, the speed of approach is going to be V cos theta. The speed of approach is V cos theta. Right? I hope you are able to understand the situation. So that V cos theta is what is bringing that particular object closer towards the wall. Okay, now I'll take another example and I'll slightly increase the complexity where both the objects are going to be moving, and we'll try to understand what is meant by speed of approach in that particular case. So now let's consider again a wall and a ball. Okay? But now, let's say not a wall. Wall means you might think that it is fixed. So instead of a wall, I'll say that it's a cardboard. Okay? There is some kind of a vertical cardboard. Okay? And that cardboard is moving in this direction over here. With, say, I'll take even values. Say it's moving with a speed of 10 meter per second, and with the horizontal, it makes an angle of 60 degree. Alright, so the cardboard is moving like this. Okay, that vertical cardboard moves in this manner with 10 meter per second, making an angle of 60 degree with the horizontal. Okay, and there is a ball. Okay, and say this ball is moving in this direction, like this. Let's say I'll draw it like here. Okay, it is moving with a speed of, let's say 4 root 3. Okay, I'll take it like this. It is moving with a speed of 4 root 3 meter per second, and it is making an angle of, say, 30 degree with the horizontal here. Alright. So both the objects are moving. So after some time, what will happen? The ball moves like this, the cardboard will be moving like this, and they will come and collide. Okay, so collision is going to take place. Both are approaching each other. So for this particular case, now clearly you try to first visualize whether this is a 1D case or a 2D case for collision. Okay, to differentiate between 1D case and 2D case, you see what happens when collision is going to occur, and then at that instant draw the line of impact. So when these two come into contact, that is the cardboard and the ball, okay, when they come into contact, that will be the line of impact, the common normal for both the objects. So this being the line of impact, and the ball's velocity is in this direction, the cardboard's velocity is in this direction. Clearly, velocity of both is not along the line of impact. So it's a case of a indirect collision, okay, between the ball and the cardboard. Now, like we saw in the previous case, which velocity is going to cause approach between the two objects? Now, to find out what is going to be the speed of approach in this case, you take the velocity components of both the objects. Okay, now suppose say you take this velocity and resolve it in the vertical direction, or that is perpendicular to the line of impact. Okay, vertical direction is perpendicular to the line of impact. So if I resolve it, okay, I will just draw it like this. Okay, this vertical component is going to be 4 root 3 sin 30. Okay, and sin 30 is half. So 4 root 3 into sin 30, this component will be 2 root 3 meter per second. And along the horizontal, if I take the component, it is 4 root 3 cos 30. So 4 root 3 into root 3 by 2. So that becomes 6 meter per second. So along the horizontal, it has a component of 6, and along the vertical, it has a component of 2 root 3. Similarly, we do for the cardboard. So for the cardboard, it is 10 cos 60 in this direction. 10 cos 60 is 5. Okay, and in this direction, it is 10 sin 60, 10 root 3 by 2, or it is 5 root 3. Okay, now clearly, this 2 root 3 and 5 root 3, let's say for example, okay, if this 6 and 5 had not existed, only 2 root 3 and 5 root 3 had existed. That is, this ball, if it had moved in this direction with 2 root 3, and this cardboard had moved in this direction with a speed of 5 root 3, then the distance between the cardboard and the ball, that is from, you drop a perpendicular from the ball to the cardboard, the distance between the cardboard and the ball will never change if only 2 root 3 and 5 root 3 had existed. Okay, so in fact, whatever value you had, if you had any value, 2 root 3 is the value which turns out for 4 root 3 and 30 degree. Now, irrespective of whatever value you have over here, that is those velocities which are perpendicular to the line of impact, they will never cross any approach between these two objects. Okay, it is the velocity components along the line of impact which is going to cause the approach between the two objects over here. So 6 and 5, okay, they are moving like this, okay, in the horizontal direction or along the line of impact. So along the line of impact, there is a velocity of 6 here and there is a velocity of 5 here. So when these two come closer together, they will come with a speed of 6 plus 5, that is the speed of approach here. Okay, so speed of approach is going to be 11 meter per second. So what you do, you take the velocity components along the line of impact and then you try to find out what is going to be the speed of approach. Similarly, speed of separation we will be able to write for the two objects after the collision has taken place. So for that I will just draw another diagram. We will try to understand through another diagram how to write speed of separation. Okay, now let's say two objects, they have collided and just after the collision, so this is one object and this is one object. Okay, now after the collision, say this object moves in this direction and say this is moving in a direction like this. Alright. So this could be an example where there are, you have seen carom boards, right, with strikers and coins. So that is a carom board striker and that is a coin. So that say carom board striker, it moved like this, it came and it comes and collides with this, and after the collision the carom board striker is moving like this and the coin is moving in that particular direction. And this is the line of impact. So this is after collision, they both are separating away from each other. Now let's say we know this angle over here, let's say this is 30 degree and let's say the value of velocity over here, so that is 10 root 3. And let's say here this angle is some 45 degree and this value of velocity, I will say take it as 4 root 2 okay, meter per second. This is also 10 root 3 meter per second. Now resolve the velocities of both the objects which collide along the line of impact and perpendicular to the line of impact. So along the line of impact, if I resolve 10 root 3 cos 30, okay, this component will be 10 root 3 times cos 30 will be root 3 by 2. Okay, and this component will be 10 root 3 sin 30, which will be 5 root 3. Similarly for the other object, okay, this component over here will be 4 root 2 cos 45, which will be 4 root 2 into 1 by root 2. Similarly, this will be 4 root 2 into 1 by root 2, it's 4 root 2 sin 45. So that is going to be 4. Right, so now clearly note that this component 4 and 5 root 3. Okay, these two will not cause any separation between these two. It is 4 root 2 into 1 by root 2 and 10 root 3 into root 3 by 2 which will cause the separation. So here the separation will happen with a speed of, okay, so this is 10 root 3 into root 3 by 2 which is going to be 15. Okay, so that's 15 and this is 4. Okay, so it moves in this direction with 4 and it moves in this direction with 15. So the separation speed between these two is going to be 19. Since they are moving in opposite directions, the speed of separation will be 15 plus 4. So speed of separation in this case is going to be 19. Alright. So once we have figured out how to write speed of separation and speed of approach in the case of 2D collision as well as in the case of 1D collision. In the case of 1D collision, it's pretty straightforward. You add the velocities or subtract the velocities directly. There is no need to take any components. Since both the velocities are going to be along the line of impact, for the case of 1D collision, there is no need to resolve and take components for finding out the speed of separation and speed of approach. It's only for the 2D collision case, we need to take the velocity components along the line of impact and perpendicular to the line of impact and find the speed of separation and speed of approach, whatever the case may be. After collision, if you are considering, it is speed of separation. Before collision, if you are considering, it is speed of approach. And then once you have speed of separation and speed of approach, we are going to be defining this term which is called as coefficient of restitution. And coefficient of restitution is defined as the ratio of a coefficient of restitution. Coefficient of restitution denoted with small e, that is going to be ratio of the speed of separation to the speed of approach. speed of separation to the speed of approach. That is called the coefficient of restitution. Okay, and depending upon the nature of collision, okay, this E will have different values. Now, if the value of this ratio turns out to be 1, the collision is termed as a perfectly elastic collision. Okay, perfectly elastic. If E value, if this ratio lies between 0 to 1, is strictly lying between 0 to 1, then the collision will be termed as inelastic collision. If the value of E is exactly 0, it is called perfectly inelastic. Okay, now there is also a situation where this E value might turn out to be more than 1. Now, those cases are not going to be for cases where rigid objects are involved. Okay, now I can just give you the name for this. When E greater than 1, the collision will be termed as super elastic collision. You know, super elastic collision happens in cases where, say, a person is going to jump and comes into contact with a trampoline, and then the person again bounces back into the air, right? So that trampoline is kind of a stretched elastic membrane, where collision is going to take place with that stretched elastic membranes. Such kind of collision will be termed as super elastic collision. We will not be taking up this case at all. We will only be discussing these 3 cases for now. Okay, I will try to make some other video at a later point in time with regards to super elastic collision. Now, I will just take one simple example of indirect collision and just discuss some basic things. Alright. So, let's say we take an object and it is projected from the ground with initial velocity u, making angle theta. Acceleration due to gravity is vertically down. So what is going to happen? This will travel in a parabolic path and then it is going to come and collide with the ground over here again. So this is where the collision takes place, when the object comes into contact with the ground again. So when it comes into contact with the ground again, okay, this velocity is going to be u, like this. Okay, and this angle will be theta, and clearly the line of impact is this line. Alright, so after collision, I'll draw the diagram here and it is bouncing back from the same position, but I'm just showing it in the diagram over here. Let's say it bounces back like this. Okay, with some velocity v, it is bouncing back, making some angle beta with the horizontal. Alright, so now which is the line of impact? Collision is happening over here. Okay, so clearly line of impact is the common normal. So line of impact is this vertical line over here. This dotted line, that is the LOI, line of impact. Okay, and this velocity u, we can resolve it along the line of impact and perpendicular to the line of impact, and along the line of impact, whatever velocity you have, that velocity is bringing the object closer. So if I take this component, this is u sin theta, and along the horizontal, this component will be u cos theta. And similarly, after impact, the velocity of the ball has become v, making an angle beta with the horizontal. So along the line of impact and perpendicular to the line of impact, I am going to resolve the velocities. So this one is perpendicular to the line of impact. This component is going to be v cos beta, and this component is going to be v sin beta. So clearly, before collision, okay, u sin theta, that is the speed of approach, because the other object, which is the floor, it is at rest. So speed of approach is u sin theta, and speed of separation is v sin beta. After collision, it has velocity v sin beta there. Okay, so v sin beta divided by u sin theta, speed of separation. In fact, if you want, you can write like this, minus 0, because the floor is at rest, minus 0. So speed of separation by speed of approach, this will be equal to the coefficient of restitution.
So if this E value is given, and let's say you know U value, theta value, okay, you can go about figuring out with one equation. You will be able to get the value of V and beta. Okay, so such cases I'll take it up in later videos. Yeah, I'm just trying to explain how to write the speed of separation and speed of approach, and how that ratio is going to be the coefficient of restitution. Okay, so that's just a simple indirect collision case where one object is fixed, that is the floor, and there is a projectile thrown, it comes and collides over there. Okay, a simple example of a 2D case. Alright.